Hello and welcome to this video about refraction. In this video, we're going to look at refraction in terms of rays and in terms of waves and wavefronts. We'll look at what the index of refraction is, Snell's law, and some interesting phenomena due to refraction. So what is refraction of light? Refraction is simply the bending of the light as it travels from one medium to another. Why does this happen? Well, refraction will occur when the velocity of that light changes as it travels from one medium to another. So when the velocity, let's say, of light in air right here, when that light ray hits maybe glass or water, that velocity will change and it causes refraction or bending of that ray. If we extend the normal into the medium as shown right here, we call the angle in between the normal and the incident ray the angle of incidence, and we call the angle between the normal and the refracted ray the angle of refraction. So how can we predict how the light will bend? Well, let's take an example. Let's look at light traveling from air into glass. And something to note, light travels faster in air than it does in glass. So we're going to have refraction occurring. When light is moving from a material in which its speed is higher, like air, into a material where its speed would be slower, like glass, then the ray will bend toward the normal. Here's the normal, and you can see that the ray is bending toward that normal. If the opposite occurs, if instead of the ray traveling this direction, if we reverse that and we say the ray is now going to travel this direction, when light moves from a material in which the speed is slower, like glass, and it is going into a material where the speed is higher, like air, then the ray is going to bend away from the normal. And incidentally, if the incident ray is parallel to the normal, if we were to have a ray coming directly parallel to this normal, then no refraction would occur. It would simply pass straight through both mediums. Here is just a nice little example of light refracting as it travels from the air into the glass. It is, if we draw a normal, you can see that light is bending toward the normal here. And then when this beam of laser light is now exiting the glass or the plastic and traveling back into the air, you can see that it is bending away from the normal because it is going from a slower speed to a higher speed. Let's take a look at refraction in terms of wavefronts. So if we have light passing from one transparent medium into another, we can think of it as traveling in terms of plane waves. Here we have air and this is water. And the light ray is perpendicular to these plane waves that are traveling. Notice the difference in the wavelength or the space between the wavefronts. Here, this is the wavelength of the light in air. Here's the wavelength of the light in the water. You can see that in the same time interval, shorter distance is moved as the light is traveling through the water. So light is traveling more slowly through that water than it is through the air. This isn't very interesting because, of course, the light ray is parallel to the normal in this case. What happens if we tilt this and we come at an angle that is not parallel to the normal? You can see that as part of this wave front, this plane wave hits the water, this part will be slowed down, but this part has not yet hit the water. It is not entered that second medium, so it continues to travel fast through this air right here, and that bends that wave. Another example of this that would be sort of a more tangible example would be thinking about a barrel that's rolling down some concrete. Here is this barrel, it's rolling on the concrete, and let's say it hits the grass at an angle. So we have the barrel rolling. This part of the barrel is reaching the grass first. It's going to begin to travel slower than this end of the barrel, causing the barrel to turn. And therefore, the path of that barrel's travel would be bent. Now let's take a look at something called the index of refraction. The index of refraction is a number, that represents the property of a material, and it indicates how the speed of light in the material is compared to the speed of light in a vacuum. So if we look at the speed of light in a vacuum as being precisely 1.00000 meters per second, how will the speed of light in other materials compare to that? And here are some indices of refraction for some different materials. For example, air is very close to the index of refraction of the speed of light in a vacuum. It is actually equal to 1.000293. We usually just round that to 3 sig figs, 1.00. So it's very close to the speed of light in a vacuum. And here's some other materials with their indices of refraction. The larger the index of refraction, the slower the speed of light will be in that material. Now let's look at how we calculate that index of refraction. Let's take a look at how to calculate the index of refraction. The index of refraction is represented by a lowercase n, and it's equal to the ratio of the speed of light in a vacuum divided by the speed of light in a particular medium. So in a vacuum, the speed of light is always the same, 3.00 times 10 to the 8th meters per second. But in different mediums, the speed of light will be different. And so comparing these two will give us this index of refraction. Since the index of refraction is a ratio, it is unitless. And that brings us to Snell's law. Snell's law is a wonderful mathematical relationship that enables us to determine the angle of refraction. If we know how fast the speed of light travels in the two different mediums that we are looking at through which the light is traveling, we can calculate the angle of refraction from that, because we will be able to calculate the index of refraction for each of those, and we can find out how much light will refract as it passes from one of the mediums to the other medium. Let's try an example together. Find the angle of refraction of a ray of light that enters a diamond from the air at an angle of 15.0 degrees to the normal. I'm going to draw a little picture of this to help us better see it. Here's our air and our diamond. Here's my light traveling through the air and entering the diamond. This is supposed to be my normal line. There's my angle of incidence, and this would be my angle of refraction. I know my angle of incidence has been given to me at 15.0 degrees. I know the index of refraction for air is 1.00. From the chart on the previous frame, I know the index of refraction for diamond is 2.42. I can plug my values into this equation right here for all these things except for theta r, my angle of refraction. That's what I would like to find, and so there's my variable. As I start to plug through the algebra, I end up getting theta r is equal to 6.14 degrees, and that's my angle of refraction. So one more idea to discuss in this video is that objects appear to be in different positions due to refraction. And you know that from the first picture where the pencil is in the cup of water, and we have refraction causing the object to look like it's in a different position. And why that is it an example right here. We have a cat that is looking into the water at this fish. And the light that is being reflected off of this fish is then being refracted as it goes from the water into the air, into this cat's eye. And because of that refraction, the cat's brain is seeing this line drawn back. It thinks it sees the fish right here, because that is indeed where the image is forming to the cat. And because of refraction and the light being bent away from the normal as it travels from a slower speed to a higher speed, the cat is seeing that fish in a position that is actually higher than where the fish actually is. Similarly, we have the fish. If we were a fish and we were looking up at this cat, the light that is reflecting off the cat is going to then refract as it travels from the air into the water, into this fish's eye. And when we draw that line back, that fish sees this cat as really being up here. That's where the image is, because the refraction has caused this. So because of refraction, spearfishing from shore obviously can prove to be very difficult. Do you have any other ideas? How might you be a better spearfisher? Aha, I think this person has found the trick. Some advanced ideas. Why don't you try the conceptual challenges on page 565, or look for some really cool examples of refraction. There's cool refraction photography where people have captured really interesting pictures. Any other ideas or questions you might have, do a little research, come show me what you find, and I look forward to seeing you in class.